Now we will use a beam element to simulate the effect of a geofabric. A geofabric can withstand tensile force, but no compressive force, and the impact of the tension in the geofabric will alter the stress state in the ground underneath an embankment, for example. The other thing is that in this particular case here, our geofabric here has no bending stiffness. It has axial stiffness but no bending stiffness. Therefore, we simply set the moment of inertia equal to 0. And that way we can simulate a geofabric with a beam element. Going to GeoStudio and opening up file SIG05, the regions and the problem has already been defined. Under Key in Materials, we have here the foundation material and an embankment material. And under Key in Structural Beams, we have a geofabric, and the geofabric has been given a Young's modulus, a stiffness, and it's been given a cross-sectional area per meter into the paper, but notice that the moment of inertia is 0. As a consequence, it has no resistance to bending. Moreover, the geofabric will only allow tension, not compression. If the embankment settlement should be such that the geofabric goes into compression, well, it cannot withstand any compression. As a result, allow compression has been unchecked in this dialog box. The first thing to do then is notice that there are no results, so we need to calculate the first analysis, which is an in situ analysis, to establish the state of stress in the ground before we come along and do something. Now we need to go back to Key in Analyses. We'll clone the in situ analysis because it's very similar, and we'll call this placement of the first lift. And the first lift is a low deformation type of an analysis. The parent is the initial in situ stresses. We get our initial stresses from the parent, and we have ignored any pore water pressure in this illustrative case here. We need to then say draw materials, and we need to apply our material representing the first lift. Clicking on the icon to show the body load, we see that self-weight or gravity has been applied to the first lift. We need to alter the boundary conditions for the low deformation analysis. Draw boundary conditions, fixing the problem XY on the far right boundary condition on the line. And we need to fix the X direction where the new lift has been placed. And we need to now, as we say in finite element analysis, wish the geofabric into place by saying draw a structural beam. We only have the one structural beam, and it will be applied to a region edge, and the region edge we want to apply it is at the bottom of the fill. So now we are ready to analyze the case once the first lift has been placed. I'll click on Verify, make sure that we aren't missing any information. Clicking on Solve, we can solve for the case of the first lift. We can now repeat this for the next 4 lifts. Going back to the Define view. First of all, before we do that, going to the Results view, we see here our vertical deviatoric stress distribution. Looking at the deform mesh, it seems to be going in the right direction. Draw vectors. This is a magnification of 30 times. Let's change it to 10 times, for example, and let's keep the magnification fixed for all of the different analyses. All seems to be okay so far. Going back to the Define view, we go to Key in Analyses. We clone the first lift, call it the second lift. Now the parent becomes the first lift. All else is the same. And for the second lift, draw materials, the fill material. On the second lift, we see the cross hatching representing the self-weight of the material, and we have to apply the correct boundary condition on the left where the new lift was placed. Draw boundary conditions fixed in the X direction. Going back then to the analysis, we can do the other 3 analyses all at the same time. Cloning number 2, we have the third lift. And the parent becomes the second lift. All else is the same, and then we will clone the third lift and make this the fourth lift. And the parent becomes the third lift. And finally, one more analysis for the fifth lift. So this is the fifth lift. And the parent now becomes the fourth lift. Now we've set up all the analysis first, but this has consequences, as I noted in the previous example. Going back then to the second lift, we already finished with material and boundary conditions. We now go to the third lift, draw materials, embankment. Sorry, I meant to click draw materials, embankment on the third lift, and we have to say draw boundary conditions fixed in the X direction. Now, Sigma W will allow you to specify boundary conditions on null elements, so we could also apply the boundary conditions for these 2 layers before we assign the material. Going to the fourth lift, you can see now, however, that by assigning or creating the analysis first, we have to repeat what we did for the third analysis. Draw materials, foundation, the third one, and the fourth one. And the fourth one is the one that is now active because it is the last lift that was placed. And we have to say draw boundary conditions, fixed X for both of these layers, but we can once again do it for the null region as well. Going then to the fifth lift, now you can see what happens again when we have defined the analysis first. We have to say draw materials, foundation material for all of these lifts, and we have to say draw boundary conditions, draw boundary conditions in the fixing them in the X direction. At this stage, it's always a good idea to step through the various analyses. Once this edit box has the focus, we can use the down arrow key to step through our construction sequence, making sure we have the correct boundary conditions and activated the correct layers for each of the analyses. Clicking on Verify, we have supplied sufficient information. Clicking on Solve. Once again, as in other illustrative examples, right mouse click, select all, and analyze all the different analyses. Going to the results view then, here is our deformed mesh. That in itself is not of too much interest. The prime interest here is what has happened to the geofabric. We can say draw a graph and look at the axial force in the geofabric. To begin with, when we have the in situ stresses, of course there is no data because the geofabric did not exist. This is the axial force in the geofabric after the placement of the first lift. Notice that the maximum axial force is near the toe of the fill placement. This behavior is exhibited many times in this situation. Then we hold down the control key and click on the second lift. Once again, we note that the maximum tensile force is close to the crest of the last lift that was placed, the second lift. Also, please note that close to the toe there is no axial force, and that is because the settlement was such that the geofabric was being pushed on, in other words, was being compressed, and in our bar beam definition we said no compression. Holding down the control key, we can click on the third lift. Once again, you notice that the maximum tensile force is somewhere under the crest of the last lift that was placed. And then holding down the control key and looking at the fourth and finally at the fifth. And ultimately we see that indeed the maximum axial force is under the center of the embankment. But once again, notice that in this area here, the tensile force in the geofabric is 0. In essence, the ground has settled in such a way that the force on the geofabric is compression, and since the geofabric cannot withstand any compression, then we simply set the force equal to 0 because of the edit box that we checked when we defined the properties of the geofabric. So this then is an illustration how a beam element can be used to simulate something like a geofabric. It is in essence a structural element that can withstand tension but not compression, and it alters the stress distribution in the ground. The altered stress distribution in this illustrative case is not all that dramatic. The main purpose here has been to illustrate procedure and technique, and that was the intent here. And so we have illustrated how this can be done, and we will leave this example then at this point and move on to another case.